This is section 2.1, which is linear functions. It also connects with the AP standard 1.3, which is linear rate of change. So the first thing is to talk about the definition of a linear function. So we can think of a linear function as a polynomial that has a degree 1, and we can write it in the form either f of x equals ax plus b or y equals mx plus b. So those should be familiar. We don't often think of a linear function as a polynomial, but technically, by definition, it is. So our example here is we're going to write an equation of a line such that f of negative 1 equals 2 and f of 3 equals negative 2. So I'm going to do this two different ways. So the first thing I want to know is that if I have something written in function notation like this just means that I have the point negative 1, 2, and the point 3, negative 2. So basically this is asking me to write the equation of a line given 2 points. So there's two ways we can do this. One is with point slope form. So just to remind you, point slope form is y minus y1 equals m times x minus x1. So we can use our 2 points. First of all, we need to find the slope. So we need to find m. That's going to be, we're going to take our y2 minus y1 over x2 minus x1. So that would be negative 2 minus 2 over 3 minus negative 1. So we get negative 4 over 4 or negative 1. So if I fill in to point slope, I have y minus 2 equals my slope of negative 1, x minus a negative 1, or we can say plus 1. And then we can distribute that and put it into slope intercept. So y minus 2 equals negative x minus 1. Then we add 2 to both sides, so we get negative x plus 1. So that's using point slope form. We can also use slope intercept. So slope intercept, remember, is y equals mx plus b. So if we know that the slope is negative 1, we can use either one of our points to plug in the x and the y. So I'm going to use this point right here, and I'm going to say 2, because that's my y, equals negative 1 times negative 1 plus b. So 2 equals 1 plus b, so b has to equal 2. And I can just plug those values back in. Y equals negative 1x, or just negative x. Sorry, b doesn't equal 2. Whoops. B equals 1, because if we take 2 minus 1, we get 1. There we go. So two different ways solving the same problem. You can use point slope or slope intercept. Okay, the next thing is to talk about transformations. Again, in a traditional sense, we don't typically talk about transformations of a linear function. We talk about the slope and the y-intercept. So you can see A is in slope-intercept form, but we can treat this as the negative means that we have a reflection across the x-axis. The 5 technically tells us that we have a vertical stretch. And the plus 1 tells us we are shifting up 1. Now, over here, part B, it's written kind of in our transformation parent function notation. So the 2 would tell us we have a vertical stretch. The minus 3 would tell us that we're shifting right 3. And the minus 4 tells us we are going down 4. And of course, we could rewrite this as 2x minus 6 minus 4, or 2x minus 10. And then that would be a vertical stretch still by a factor of 2 and a shift down 10. So these two are equivalent forms And they're going to look like the same line, but depending on how we write the form of the equation, it's going to look slightly different. Okay, so next is talking about average rate of change. So we know average rate of change is just a fancy way of saying slope. So for a linear function, the average rate of change is going to be constant. It's going to be the same number no matter where we're at. So if we look at this example of a table, if we want to find the average rate of change on the interval, or between x equals 1 and x equals 5, we're looking at this value and this value. So it's again our y2 minus y1 over x2 minus x1, so that'd be 160 minus 40 over 5 minus 1. So that'd be 120 over 4, which gives us 30. So our average rate of change would be 30, and something to note that no matter what two values we pick in our table, since it's a linear function, it's going to have a slope or an average rate of change of 30. Okay, the last thing is talking about how can we use our calculator. So these are the directions. You can pause it if you want to look at these longer, but to find the linear regression, we're going to enter our table into the stat feature, and then we're going to use calc and linreg, so linear regression. So I'll show you really quick on the TI-84. So you would go to stat, edit, we're going to clear. Okay, so in list 1, I'm going to put the 1, 3, 5, 7, 9. And then we're going to do 40, 100, 160, 220, 280. Okay. Then we're going to go to stat again. We're going to right arrow over to where it says calc, and we are looking for linreg, linear regression. You'll notice there are two linear regressions. So one of them says down at 8, it says a plus bx. We want the one that's ax plus b, or think of our mx plus b. So we're going to hit that. We're going to hit enter, and there's our equation. You can see our a value is 30. Our b value is 70. That's not right. Let's check that again. Okay. Stat calc. Oops. Let's go stat calc linear regression. We got list 1 and list 2. That is not right. Okay, so something's going on with that. It should be, if we did it on our actual calculator, we should get 30x plus 10. So our b value is wrong on that. So something's going on with this this app. But so the correct answer, if we go back to our thing, should be, we should get y equals ax plus b. You should get that the a value is 30 and the b value is 10. So we should get y equals 30x plus 10. I'm not sure why the app is giving us the incorrect, but you can double check that on your calculator. And then also the other way to do this is to go to Desmos and put in your table and then use the regression, the linear regression, and you should get the correct value for that. Okay.